Okay, so last time we were discussing this system, regenerative cooling system. I think we covered the theory, regenerative, where we take part of that air coming out of the cooling turbine and use it here in this heat exchanger. Okay. So we covered this theory. Now there are different mass flow rates involved. Here is the mass of air which is flowing. Let me name it M1, M dot 1. Here after cooling turbine, some mass is taken out of this cooling turbine and we use it here in this heat exchanger. So it is, for example, represent, no, this was M dot 1, right? This one I am naming it as M dot 2.
But isn't M dot 1 split into M dot 2 and M dot 3?
Yes, here it is splitted. M dot 1 is splitted in M dot A and M dot 2.
No, I mean, this part here. There is no splitting also?
Yeah, there is a splitting, but I'm taking, yes, you're right. This M dot 1 starts from here. Yeah, okay, right. Yeah, there is a splitting also. So actually this M dot we take out from the compressor. What is that compressor? Main jet engine compressor. So we should start M dot 1 from here actually. From that compressor, which a small part which we are taking. Okay. So yes, you're right. We should call it from here onwards M dot 1. Now here this M dot 1 is separated into two parts. M dot A, which is flowing towards the cabin, this one, and this one which is flowing towards this heat exchanger. So I can say M dot 1 is equal to M dot A plus M dot 2. Okay. So that's what we discussed last time. Now let's solve a numerical and this will be further clear. So here our regenerative air refrigeration system, which is designed to take 18 tons of refrigeration load. So this 18 tons represent the Q dot cooling of the aircraft cabin. The ambient air at pressure 0.82 bars and temperature 12 is rammed isentropically. So this represents which point in the figure? Ambient air means this is P1, T1, this one. It is rammed isentropically till the pressure rises to 1.22 bars. So what is this point? This is point 1. Now pressure is raised isentropically. Rammed means inside the diffuser. So this is P2, this one, pressure rise during ramming, right? The air bled off. Bled means here taken out from the main compressor. So this air which is taken out or bled off from the main compressor at 4.4 bars means P3. This is P3. Okay, maybe in the exam this schematic is not given. So first you have to draw the schematic, number it. Now you will know which point is which number, right? So here it is already drawn, but you have to draw it, okay? And then whatever numbering you choose, accordingly you will see which one is P1, which one is P2, which one is P3. So according to this diagram, now this is P3. The air bled off the main compressor at 4.4 bar. So means it is talking about point 3. Is cooled by the ram air in the heat exchanger. Which heat exchanger? This one, where this air is cooled by this rammed air. So for this heat exchanger, effectiveness is given for this one. Effectiveness is 0.62. The air from the heat exchanger, from this heat exchanger, is further cooled to 64 degrees Celsius in the regenerative heat exchanger. The second heat exchanger, this one, here it is further cooled, so it means T5 is given. 64 degree Celsius. How it is cooled? With a portion of the air bled after expansion in the cooling turbine. With this air, which was bled or taken out from the turbine. With this air, it is cooled from 0.4 to 0.5. 0.4 temperature, we do not know yet, but 0.5 temperature, it is given 64. The cabin is to be maintained at a temperature of 22. Which point? 7. So this is T7. And pressure of 1 bar means P7 and T7. If the isentropic efficiencies of the compressor and turbine are 88% and 82% are given, determine the following. So before determining all these, let's show it on TS diagram. Starting from point 1, this is P1, this is P2, this is ramming 1 to 2, then 2 to 3, compressor 2 to 3, and isentropic efficiency is given, so I should show the non-isentropic part. So 2 to 3, 3 dash, then 3 to 4 cooling, constant pressure cooling, 3 to 4, then 4 to 5, another constant pressure cooling. So it will end up somewhere here. Better to show arrow so that we know where the fluid is going. At 0.5, it enters into a turbine. It is cooled to some low pressure. Let me show 0.6. Isentropic efficiency of turbine is given. So show the non-isentropic part. 6 dash and 6 to some 0.7. Here is the cooling part. 0.6 or 0.7 pressure is higher than ambient pressure. Temperature, it seems like T6 is lower than T1. Maybe it's not, maybe it is. We have to see. Look here, 0.1 temperature is 12, right? It means, and look, 0.1 pressure is 0.82. It means aeroplane is not at a very large height. 0.82 bars. What is the ambient pressure on ground? 1 bar. So it is a little smaller than 1 bar. So it means it is not at a very large height. That's why ambient is still Only 12. Right. Okay. So then zero point 0.6, maybe it could be less than 1. We do not know. We'll see. What is the temperature at 0. 0.6 after turbine? Okay, so far any questions? Because this is the half of the question which we have solved. Schematic and TS and showing all the points. Right. Maybe in the exam you will have 5 marks for that one, 5 marks for this one. Now we will solve the next three parts. Okay, if it's clear, now let's solve. First part is to find out the mass of air bled from the cooling turbine to be used for regenerative cooling. So which mass we are talking about? M1, MA, M2. We have shown three masses, M1, MA, M2. So which is this one? M2. So we need to find out M2. Okay. So now we need to think about what are the equations which can give us this m dot 2. What about m dot A, the mass of air which is flowing towards the cabin? How we used to calculate m dot A in previous questions? This m. MCP delta T, but which Q? Q is equal to MCP delta T. Which Q? Load, refrigeration load. How much is the load? 18 tons, that is given here, which you are calculating nowadays. The same procedure which you are doing nowadays for a room, the same you can do it for aeroplane. It's also space. Okay, so all the heats which are entering, you will do it for the most for an average condition or for the worst condition, right? Okay, so using this q dot is equal to, I can write it m dot ACP, which temperature change? T6 minus T7. And here I can replace m dot A with yes, T7, yes, better to write it T7 minus T6. And m dot A, can I write it as m dot 1 minus m dot 2? Okay, this is one equation. From here, m dot 1, m dot 2, both are unknown. So I need another equation. So then, because we want to find out m dot 2. So here, what about this heat exchanger? If I write energy balance across only this heat exchanger, I will have another equation involving m dot 1 and m dot 2. So what will be the equation of this heat exchanger? Thermodynamically, not heat transfer equation. Heat transfer equation is UA delta T. What is the thermodynamic equation of this heat exchanger? MCP delta T, but there are two fluids. One fluid is this one, other is this one. So E in is equal to E out. So both, whatever is entering is equal to leaving. This is the thermodynamic equation. So here I can write m dot 1 Cp. What is the temperature change from 4 to 5? T4 minus T5, that is the heat lost by m dot 1, is equal to heat gained by m dot 2. Cp, what will be the temperature change?
8
T6 minus T8 or T8 minus T6 because it will absorb heat. This fluid will absorb heat, this fluid will gain heat. No, the other, this fluid is losing heat, this is absorbing heat. So T8 minus T6 or T7? T6. So here we have another equation from this heat exchanger involving same m dot 1, m dot 2. So now we have two equations, this one and this one. We can solve both of these simultaneously to find out m dot 1 and m dot 2. But before that, we need to know all these temperatures. T5, T6, T7, T8. T8 is, by the way, given here. Assume the temperature of the air leaving to the atmosphere from the regenerative heat exchanger is, that is T8. Okay. If this temperature is not given, then you will decide something. Sometimes some temperatures are known to us, or it is our requirement to reach that temperature, right? Sometimes we have to decide. If we decide such a temperature that your heat exchanger size becomes too large, so we have to compromise on that temperature. So the whole design procedure involves so many other things which we cannot discuss here. So some are given, some we have to calculate. So T8 is given here, but other temperatures we have to find out. And you know the procedure, start from point 1, 2, 3, 4, 5, start solving the equations and find out all the unknown temperatures and then put it here to find out m dot 1 or m dot 2. Okay, any questions so far? It's not that difficult, but you just need to practice all these questions, okay? If you can make the schematic and TS diagram correctly, then it's just a matter of solving equations. What are the equations? There is no complicated equation. MCP delta T, or second one is T2 by T1 is equal to P2 by P1. These are the two equations, that's all. There is no other, or heat exchanger equation. Again, MCP delta T of this fluid is equal to MCP delta T of other fluid, right? So do not expect MCP delta T in formula sheet. Maximum you can get in formula sheet this equation of T2 by T1 is equal to P2 by P1 to the power gamma minus 1. Okay, this equation can be given. The rest is MCP delta T, or M into delta H in previous chapter 3. Okay. Okay, so now I will solve it. Here is the given data, which we have now. Start calculating these temperatures starting from point 1. So first calculate point 2 temperature, isentropic compression. So this is T2. Then next another isentropic compression, calculate T3, and here isentropic efficiency is given. So here T3 dash. Even this equation is not required to be given in the, you should know what is isentropic efficiency of compressor. Isentropic over actual. And actual over isentropic is turbine. Okay. These are simple definitions, not equations. Okay, so till this point, now we have calculated T3. Now what about T4? Here is that heat exchanger. For this heat exchanger, what was given?
effectiveness.
effectiveness. And what is effectiveness? Actual heat transfer divided by maximum possible. So actual is T3 minus T4, MCP T3 minus T4, this temperature change, divided by maximum possible, MCP T3 minus T2, maximum possible. MCP cancels. All right. Now, for example, if you ask me to give that formula in the exam, what I should give, T3 minus T4 or T5 minus T6 or T7 minus T8, what? That I do not know what numbers you have chosen. So no effectiveness formula. You should know if actual over maximum. All right. Because in this course, the issue is formula sheet, formula. So many messages I will be receiving, formula sheet, upload the formula sheet. But which formula? Okay. So it's effectiveness. You should know actual over maximum. Similarly, isentropic over actual or actual over isentropic. That's all. Okay. So from here we can find out T4. T3 we already calculated, T3, T2 already calculated. So we can find out T4 from effectiveness. Effectiveness is given 0.62. So here is T4. Then T5 was also given, that in this heat exchanger, temperature is reduced to this much. T5 was given. Then from T5 to T6, another isentropic. So find out T6, and isentropic efficiency is given for a turbine. So find out T6 dash. Okay. So all the temperatures are now known. T7 is already given. Any questions so far? Okay, now all the temperatures are known. Now those mass flow rates which we want to calculate. So it is clear what is m dot A, the air going to the cabin. M dot 1 going towards the heat exchanger from the turbine. Sorry, m dot 2. M dot 1 is the air coming from the main jet engine compressor. M dot 1. Those are explained here. Now write the equations which I already told you. So first of all, this equation m dot A is equal to m dot 1 minus m dot 2 is equal to refrigeration load divided by refrigeration process, which is T7 minus T6 dash, right? Here, look, 14,000, he is multiplying with 14,000 to convert this tons into kilojoules per hour. So I would recommend you to keep your life simple. Always use tons multiplied by 3.5 kilowatts. Keep it in kilowatts. If you will follow the exact solution in the book, sometimes he is using kilojoules per hour. In some question, he is using kilojoules per minute. In every case, you have this different number here. So leave the book. So use your.
What is 14,000?
It is to convert this tons into kilojoules per hour.
I think it was 12,000.
12,600. Okay, so yeah, maybe it's wrong. That's why I'm telling you, just keep it 3.5 multiplied by Q. Yeah, it was, I think, 12,000 something. Yeah, yeah. So you need to correct it. So when you are using 3.5, it means your answer in kilowatts, and you will have here kilograms per second. Here kilowatts, kilojoules per second, so answer will be in kilograms per second. But here you will have a very large number. No, look, kilograms per hour is 4,700 multiplied by 3,600, so it will be a very large number. That's why he's using hours per hours. And yes, you are right, that is also wrong. It was not 14,000, it was 12,000 something. Anyway, so this is equation 1. What was equation 2? from this heat exchanger, which we discussed already, write the heat exchanger equation. So here we have the second equation. This one is equal to this one. E in is equal to E out for that heat exchanger. By putting values, here is that equation. Now you solve these two equations simultaneously. You will calculate m dot 1 and m dot 2 in kilograms per hour. Okay. Now everything, that's what we needed to calculate, m dot 2. Next part is to calculate the power of compressor. Here, so here it is m dot 1, Cp of T3 dash minus T2, compressor. T3 dash. Again, this was in kilograms per hour divided by 3600, so you get the answer in kilowatts. Otherwise, it will be kilojoules per hour. So be careful when you are solving it at home, when you are practicing these. So do whatever you feel easy. Easiest is 3.5. The other conversion factors I will not give in the exam. Okay. So just follow kilograms per second. Okay. This one you can remember. 1 ton is equal to 3.5 kilowatts. We are not solving any English unit so far, but in English unit, 1 ton is equal to 12,000 BTU per hour. This is something we all try to memorize in kilowatts and BTU per hours. Okay. If you see, there is a sticker on this air conditioner, and there is rating will be given either in tons or BTU per hours. If I try to read here, here it is given in BTUs per hour, 23,000 something BTUs per hour. So how much are tons? About 2 tons. Here it is written BTU per hour. And also there are some more important information. Meter cubes per hour is also given. Meter cubes per hour. Flow rate at the inlet of compressor. How much volume compressor is dealing at the suction side of compressor. That is also written here. 125 meter cubes per hour. The rest electrical data, this much kVA and etc. Power of motor. Okay. And the type of refrigerant will be mentioned somewhere. Written both in Arabic and English. I cannot read the type of refrigerant that is normally also mentioned, R11, R22, etc. But nowadays R11, R10, R22, those are banned. Now new refrigerant, in only old refrigerators you will see those R22 or R11, not in modern air conditioners. Okay. So BTU per hour is a very common term which is used. So 2300, so it means 2 tons, this one 2 ton, 4 ton AC is installed here. Okay, so when you are calculating this cooling load for this room, and now it comes out to be 15 tons, for example, so there must be something very wrong in your calculation, or it comes out to be 1 ton, 1.5 tons. That will give you some indication whether your calculation seems to be wrong or not. Okay. And next you calculate COP. Okay, so that is done. Now next, last configuration, which we will just go through quickly, that is reduced ambient air refrigeration system. Another configuration of air cycle refrigeration system. What is the different thing you notice here in this diagram? Yeah, this turbine. So this ram air in the previous configurations, it was directly going towards that heat exchanger. But here ram air is first cooled in a turbine, then it is sent to that heat exchanger. That is different. The rest is same as the simple cooling system. So we have covered simple cooling system, bootstrap type cooling system, then regenerative, and now this one is reduced ambient air refrigeration system. Okay, because at very high velocities, for example, when the aeroplane is moving in or rocket is moving at supersonic velocities. You remember that equation which we developed for diffuser part? T2 by T1 is equal to something in terms of Mach number. In that equation, that Mach number was there. What was Mach number? Representing the velocity of that object with respect to velocity of sound. Mach number greater than 1 means supersonic velocity. Okay, so here as the Mach number increases, what happens to this one? Increases. So maybe at a very high velocity, this T2 becomes too high and it cannot cool that fluid effectively. So what we do, we first cool it in a turbine and then we use it in that heat exchanger. So this type of system is normally used when your airplane is moving at very high velocity in supersonic range, right? That is the only difference. The rest is same. Now in this heat exchanger, after this heat exchanger, there is a turbine and then it is sent to the cabin. Look at the TS diagram. TS diagram is very much similar to simple cooling system. Look, 1 to 2, okay, ramming, 2 to 3, 2 to 3 compression, 3 to 4, 3 to 4 cooling. But this process is not shown here because this is a separate air. Our TS diagram is drawn for which air, which is leaving that compressor, not this air. That's why it is not shown here. This process 2 to, let me name it 2 to B. What will be 2 to B? There will be a separate process 2 to B, maybe like this, if you want to show it, from 2 to B. Not like this. We shouldn't show it, but if you want to understand what is happening. So 2 to B, it is isentropic expansion. So it cannot be like this, something like this. 2 to B. Now there is a heat exchange between 3 and this fluid at point B. Clear? 2 to B. 2 to B, isentropic expansion in a turbine. Now between 3 dash and B, there is a heat exchange between 3 and B. Actual point is 3 dash. There is a heat exchange. And the temperature of this 3 drops. Temperature of point B will increase like this one. B to exit. Because where this air is going? Exit. And the work of this turbine and the work of this turbine, both are used here to make this ram air go out. Exhaust. Okay. What is this thing? Are you studying design?
Yes.
This is a type of gear, bevel gear. if both are at right angle to each other. If, okay. So that is reduced ambient air refrigeration system. All those processes are clear. There is nothing difficult. We have already. Now here is a comparison of all the types of air cooling systems which we have covered. As a function of what? DART. What was DART? Remember anyone? Dry air rated temperature. What was dry air rated temperature? The air which is entering the cabin after turbine when it is entering into the cabin. That temperature is called dry air rated temperature, which we defined in the initial slides. So here you see dry air rated temperature as a function of Mach number. Okay. So you see here, for example, this is what we want, for example, for normal passenger aircrafts or lower than this, but maximum at least at 20 degrees Celsius air must be entering for cooling purpose. You see normal passenger aircrafts, their velocities are in this range. As far as Mach number of 1 means what? Velocity of sound. So actually they are normal aircraft, they are moving in this range most probably. Now in this range, your simple cooling system can give you good enough DART, right? These two can give you DART, but much lower than in negative. What are these two? Bootstrap and regenerative cooling. But if you are taking some food products with you, frozen products, so then a simple cooling system may not give you such low temperatures. So then you have to use bootstrap and regenerative. Now supersonic velocities in this range, your simple cooling system cannot provide you the required, because now look at the temperatures. So you have to go for these two or reduced ambient if the Mach number is so high. Okay. This graph is clear. So that has been discussed. If airspeed, or airspeed here means the speed of your aeroplane is greater than 1000 kilometers per hour. So 1000 kilometers per hour means higher than Mach number of 1. You have to go for these two or reduced ambient air. Reduced ambient air may be useful only for supersonic aircrafts and rockets. Okay. Here is another diagram that is giving us what? Simple cooling system, just see here. And this one, simple cooling system with evaporation. We saw one configuration if we take an extra fluid with us. For example, some liquid oxygen or liquid nitrogen, right, which can evaporate. So then we can get very low temperatures, DART, even with simple cooling system. Okay, same you see here, reduce this bootstrap with evaporation system. This was normal bootstrap system, but bootstrap with evaporation can give us very low temperature, depend upon which type of evaporating fluid we are taking with us. So you can create that liquefied gas, for example, liquid nitrogen and liquid oxygen on the ground using cryogenic refrigeration system and take it with the aircraft. Okay. So that is the summary of all these systems which we have studied. Which one is better for which application we can generally, these are the just typical values are mentioned here, typical curves for different types of air cooling systems. That's all. So that is what we have covered in this chapter. These are the practice problems. This one problem, some solved examples from this book, R.S. Hurmi, I've already uploaded, shared in Teams, one PDF. And this one you already have, Sanjal's book, same refrigeration chapter 11. These are some problems related to air cycle refrigeration. Okay, so these are your practice problems for this chapter. Okay, then we solved some more problems in these slides which were not from here. Okay, so this is complete chapter 5. Yeah, this is wrong. This is air cycle refrigeration. I will check it. So with this chapter is finished. Now we'll start the next chapter, chapter 6. So chapter 3, 4, 5 is for test 2 exam. Okay. This chapter, chapter 6, is for those who will appear in retest. Whoever will appear in retest, so whatever we will cover in next 2 weeks, that will also be a part. So do not appear in retest this time. Okay. Retest means chapter 6 is also included. 3, 4, 5 and 6. Okay. Whatever we'll cover in chapter 6 will finish in 2 weeks. Okay. Clear? Whatever will be the reason, this chapter will be included for retest of test 2. Okay. So now let's start the next chapter, chapter 6. This chapter is about absorption refrigeration system, another type of refrigeration system. So far we have covered vapor compression and air cycle refrigeration system. Now this is another one which is called absorption refrigeration system. This system is not as common as these ones, of course, vapor compression systems, but still those are being used. And what is the best thing about this type of refrigeration system is that to run these systems, we do not need a lot of electrical energy like in these systems. Because in vapor compression system, a major part of energy, not major, all the part of energy which we require is in the form of electrical energy to run this system. The electrical energy which we provide in the compressor. In these systems, absorption refrigeration systems, what we do, we replace compressor with something else which do not require electrical energy, which requires heat. Just heat. Heat by burning anything. Coal, you can burn coal, oil, gas, burn wood, anything. You need heat in the form of, you need energy in the form of heat, not electrical energy to run these systems.
There is no need for compressor.
No. In these systems, we are replacing compressor with a new device, which we will see, which does not mainly need electrical energy. It mainly requires heat. Okay. And that heat can be provided using solar energy, solar thermal energy, not photovoltaics. Okay. That is the major advantage, but that is not feasible to use here. For example, here if you use vapor absorption system, so something outside is burning, you need heat. Okay, so that is not feasible from a safety point of view. There will be so many burners everywhere, you will see something is burning. But those are used for large systems. Those are not feasible for small scale. When you have electrical energy, there is no need to use this one. But when you do not have electrical energy, or electrical energy is very expensive and you want to run your system on solar thermal energy in deserts, so then we can go for these systems. You need to provide heat. Okay. So now let's discuss this system. So these slides are made from these two books. Okay. First of all, we need to understand the physics of this process which is used here, where we are replacing compressor with something which does not require electrical energy. Now let's try to understand that process which occurs in vapor absorption system. The actual vapor absorption system is not like this one, but just to understand the physics behind that system, we are using this system. What is this system? Only two vessels. Now let's, what you see here, in vessel A, there is water, pure water. Because in these systems, we use more than two fluids. In vapor compression system, there is only one fluid flowing inside the system, which is refrigerant. In air cycle refrigeration, what was the refrigerant? Air. Same air was flowing everywhere. In these systems, we use two different fluids within the system, two fluids. For example, one of the fluid is water. Water is here in that vessel at 30 degrees Celsius. Ambient is also at 30. So in this vessel, you will have water, and here you will have water vapors. At 30 degrees Celsius, water vapor pressure will be 4.24 kilopascal, which we can see from the table. Because evaporation is taking place at all temperatures. Boiling is something which will occur at a particular temperature, but evaporation is taking place at all temperatures. So due to this evaporation of water, what will be the vapor pressure of water vapor here is 4.24 kilopascal. We can see from the steam tables. Okay, so in this vessel we have water liquid, and the space above the water there is vapor. So here we have a vapor pressure of 4.24 kilopascal. Clear? Next, we have another vessel, vessel B. In this vessel, we do not have pure water, we have a solution of 50% lithium bromide and 50% water. Lithium bromide is another chemical compound which is a salt. Its property is that it can absorb water vapor if it is present in its surroundings. It has this ability to absorb water vapor. So here we have 50% lithium bromide and 50% water liquid solution. Now water in its pure form and water in solution. Now it's a solution of water plus lithium bromide. So when water is mixed with some salt, so now majority of the water molecules are surrounded by or bounded by this salt. So now less water can evaporate compared to when it was all water. So when we have pure water versus when you have water plus some salt solution, here at the same temperature, 30 degrees Celsius, you will have less vapor pressure. Lithium bromide is not volatile, it is a solid normally, but when it mixes with water, it becomes a solution. But now here at the same 30 degrees Celsius, you will have less pressure because now less water can evaporate. All right. Valve is closed initially. This is the initial condition. Everything is under equilibrium. Temperature is 30, 30, 30, everywhere 30. But here you have pure water, but at high vapor pressure. Here you have water plus lithium bromide solution. Vapor pressure is low. Okay, so far everything is clear. This is initial state 1. That is explained here in 3 points. Chamber A contains water at this pressure. Chamber B contains 50% lithium bromide Solution at 30 degrees Celsius, but at some lower pressure, 1.22 kilopascal. Valve is closed, so there is no interaction between two vessels. Now, if we open the valve, here pressure was 4 point, here it was 1.22 kilopascal. So what will happen when you open the valve? So this water vapor will start to flow here, and this will be absorbed by this solution, lithium bromide, but because it was a 50% lithium bromide water solution, so it has the capacity to absorb more water and water vapor in it. So as the water vapor is absorbed here, the heat of condensation of water vapor will be released and it will become liquid here. And here this concentration will change. It will not be 50% anymore. This will drop because more water vapor is adding. Lithium bromide concentration will be lowering. Water vapor concentration will be increasing. And some heat will be produced because this, there are two things happening. Water is condensing. Second, what is happening? Water is absorbed by lithium bromide. This absorption process is a chemical process. So this chemical reaction is exothermic reaction. So there will be heat produced due to water condensation, and there will be heat produced due to this exothermic reaction. So this heat will produce this 50% concentration will be disturbed. Due to the heat produced, the temperature will rise here. Okay. Now, if by some means we can keep this 50% constant, and also we cool this fluid so that temperature does not rise. If we can do this by some means, what will happen? It will continue to absorb this water vapor. Because here, as the water vapor is absorbed, lithium bromide concentration drops, but maybe we are adding more lithium bromide to keep it at 50. During this process, heat is produced, temperature rises, and we keep that temperature to 30 by cooling it. If we can maintain this thing here in this vessel, this water vapor will continue to evaporate from this high pressure to low pressure, because here we are keeping this 50% and we are not allowing this temperature to rise, so this pressure will stay at 1.22. So after some time, this 4.24 will become 1.22 here. Corresponding to this 1.22 kilopascal, water evaporation temperature is 10, not 30. And this vessel is present in a 30-degree ambient. So what will happen? Heat will start to flow because now you have dropped the water vapor pressure in that vessel A.
This is constant pressure, or is there a vacuum?
It's only water here.
So
Only water is water pressure actually. Okay, so here heat will flow from 30 to 10. And here we will have cooling effect. This will continue until we can maintain this condition. But now what will be happening in reality? That is what we are imagining. If we can keep this condition fixed, this will happen. This liquid water will start to evaporate. And during this, but now it is evaporating at 10 degrees Celsius because pressure is reduced here. And there will be a cooling effect here. Now, what will be happening in reality? After some time, this liquid water level will drop. At the same time, what is happening here? This 50% will not be 50%. It will rise. Rise means water level will rise. Lithium bromide concentration will drop, but water concentration will increase. Now, it depends how we are defining this concentration, on the basis of lithium bromide or on the basis of water. So on the basis of lithium bromide, concentration is dropping. on the basis of water concentration is increasing. Okay. And here temperature is also increasing. So after some time, all of the water vapor will be evaporated here, and this will not have this ability to absorb more water vapor. So it means with the passage of time, this cooling effect will reduce. So we want to come back to initial condition because here water vapor is dropped. Here it has reached its maximum limit to absorb water vapor, right? So we have to regenerate whatever water vapor was absorbed here, we want to desorb it so that we can make this water come back here and repeat the process. So what we are doing, we have these vessels inside the room. Vessel A is cooling the room, vessel B is here outside the room. Now vessel A, all the water is evaporated. Now we'll bring these two vessels outside. We will regenerate that water vapor again from B to A, the initial condition. Once the initial condition is achieved, bring it again inside. So it's not a continuous cooling. Cooling, regenerate the water, bring it back again cooling, again regeneration. What is regeneration means? We will heat this solution so that water is evaporated. Lithium bromide, it has higher boiling point than water. So when you will heat, only water will evaporate, lithium bromide will stay there. So whatever water will be evaporated, because now you are heating it, so here vapor pressure will rise. It may become again 4.24 kilopascals. And here you want to condense it. This is the last process. The first was initial condition, second is refrigeration. Okay, so this refrigeration process is explained. Now regeneration. Now you are supplying heat in this weak lithium bromide solution. When you supply heat, water will start to evaporate. Air pressure will rise because you are supplying heat at a higher temperature, for example, more than about 110 degrees Celsius, so that only water will evaporate, but water will evaporate at a high temperature. Here is 110, so water is if it is evaporating at a higher temperature, but you want to condense this water vapor where? Because these vessels are placed in 30 degrees Celsius. So water vapor is produced at a high temperature, but now you are condensing it in the ambient temperature. So the condensation pressure corresponding to 30 is 4.24 kilopascal.
Where will the condensation happen?
Condensation is happening in this vessel. Here only water vapor is generating. What is left here? Strong solution of lithium bromide. It became weak. Now you are supplying heat so that water evaporates. Now water is evaporating, going back to this vessel. Now this vessel, you have taken it outside in the 30 degrees Celsius. So it will be condensing at 30 degrees Celsius. The pressure is 4.24 kilopascal corresponding to 30 degrees Celsius. So that the required amount of water vapor is condensed here. When it is the required amount of water vapor is condensed, it will again become 50% lithium bromide solution. You will close this valve. Now you will allow this both vessels to reach 30 again. This is already 30, but now you want this to reach 30 again. Once this will reach 30 again, here again pressure will drop to 1.22 kilopascal, which is the saturation temperature of this solution at 30. Initial case. Here it is still 4.24 and 30. The initial condition. Again the process will repeat. But this is how we are making the water to evaporate and move here. In this system, there is a compressor. Whatever water will evaporate, compressor will take it away and it will raise its temperature and pressure. Here, whatever water was evaporated, it was absorbed here, and then we supply heat to raise its temperature and pressure.
Our input is Q evaporation.
Yes, the overall input here in this heat which we are supplying
Our output is the
is Q cooling, which was the second step. But we cannot use this system in this way because this is not the way to cool space continuously, because this is not a continuous cooling process. It produces cooling for a little time, then we have to bring back to the initial condition by regenerating that water vapor and then cool it again and then regenerate, cooling, regeneration. So we have to make this process continuous. But the basic understanding or the basic physics behind this process is explained here. So here we have to use pairs of fluids. In this example, water is refrigerant or lithium bromide? Water, because water was absorbing heat from the space. So in this case, water is refrigerant and lithium bromide is called absorber. So in these systems, we have two fluids. One is refrigerant, other is absorber or absorbent. So this is one pair which is normally used in these systems, water, lithium bromide. Water is the refrigerant, lithium bromide is the absorbent. There is another pair which is ammonia plus water. In that pair, ammonia is refrigerant, water is absorbent. So we have to choose such pairs which has this ability to absorb the other one whenever the other one is available in vaporized form.
maybe it depends on the tea boiling.
Yes, one should have higher T boiling than the other one. Because when the regeneration process, only refrigerant should boil off, absorbent should not boil off.
The ammonia tea
Yes, is less than water. So water stays there, ammonia evaporates. Here, water evaporates, lithium bromide does not evaporate in the regeneration process. So these systems are more complicated in this way, but here the advantage is no electrical energy to run a compressor. Just need to provide heat, any heat source.
how long does the water related to the
Yeah, that's what we will now start discussing in this chapter, everything. Now, first of all, okay, we just go through by these points. I have included this explanation just to understand what is happening from A to B. There are so many processes, so many things are happening. So nowadays you have those audio, click it, it will read. You have this figure in front of you, you can understand, okay? So I've just included just to understand this process, what was happening from A to B, B to C. Now, the main thing is how to make this system continuous. What is the time? 40. 5 minutes. Now, to make this system continuous, we have such mechanism. Look, in this is an absorption cycle now. These three components are same, which we have here in vapor compression system. Only the compressor is now replaced with these components. Whatever refrigerant was evaporated is now absorbed here. In the absorber, this vapor becomes liquid, and this liquid is pumped to the generator. In the generator, we supply heat so that refrigerant evaporates and the strong solution comes back. So we are using pump and expand, because here in the pump pressure is increased. Why pressure is increased? Because we want to condense water at a high temperature. Water was absorbing at a low temperature. Now we want to condense the same refrigerant at high temperature. So we increase the pressure of the liquid, not gas. So here we have to supply electrical energy, but that will be very negligibly small compared to this heat to separate the refrigerant. But at the same time, this is going back. Now, this is a general schematic, so we will discuss it in detail in the tutorial class. Just to understand this thing better, this is more realistic picture. Here is that evaporator. Look, here is the refrigerant which is boiling. At the same time, in the same vessel, you have this absorbent fluid. What will happen? This absorber will absorb whatever refrigerant is evaporated. Now, during this absorption process, I told you this is an exothermic reaction, water is condensing, heat will be produced, so this heat must be taken out. If you do not take this heat out, the ability of this absorber to absorb water vapor will drop. So during this absorption process, whatever heat is produced, that must be removed continuously. So there is a cooling water going on. So in the same vessel, there is evaporation, here is absorption. During absorption, it becomes liquid solution. This liquid solution is here, collected at the bottom. It is pumped here to a generator. In the generator, we are supplying heat from any source. So only refrigerant is evaporated. The concentrated solution is flowing back to the absorber. This refrigerant is condensed and then it is supplied. So here you have expansion valve here. Expansion valves are not shown here clearly. That's how this process is occurring continuously. The same two vessel process has become continuous process using this mechanism. Okay, so we'll discuss in the next class where till then you can continue to watch this animation. Here all those four processes are mentioned. They are occurring continuously. Now you can easily understand what is happening here. In the evaporator, refrigerant is evaporating by cooling this fluid, chilled water. Whatever is evaporated is absorbed here. Here you have absorber. Absorbent fluid coming from the generator. Concentrated solution, this red part. Okay, so whatever vapor is there, it is absorbed here, becomes liquid. So this liquid is pumped to the generator. In the generator, we are supplying heat. Only refrigerant is evaporating. It is condensed here. This is the condensed refrigerant. Okay, so this how this process is occurring continuously. The system is working continuously providing cooling. At the same time, there is generation going on, absorption going on. There are some more components which we will study. There is a heat exchanger. Why this heat exchanger will discuss. Okay.